Section 9.3, Day 2 of Significance Test for Mean. The learning targets for this lesson are: you should be able to construct a confidence interval to draw conclusions for two-sided test about population means, and you should be able to perform a significance test for paired data. If you remember in yesterday's video lesson, we had an example where we looked at a Hawaiian pineapple company where they were trying to run a test to see if the mean weight of their pineapples was not 31 ounces anymore. They installed a new irrigation system and they were trying to see if their mean average weight had changed from 31 ounces. Below you can see a mini tab of the data that came out of this test. Confidence intervals will now give us more information than test alone, just like they did with proportions. Taking a look at the mini-tab data, you can see the t-score that we got from the test of 2.76 and the p-value at the far right of 0.008. Since this value was less than alpha, we rejected the null hypothesis that mu was equal to 31 and concluded that the mean weight of the pineapples must now not be equal to 31. But in the same mini-tab output, you will notice the 95% confidence interval for the mean weight of all pineapples grown in the field this year is between 31.255 and 32.616 ounces. We are 95% confident that this interval captures the true mean weight of this year's pineapple crop. For the pineapples, the two-sided test at an alpha is equal to 0.05 level rejected the null hypothesis of 31 ounces in favor of the alternative, which was the mean is not 31 ounces. The corresponding 95% confidence interval does not include 31 as a plausible value of the parameter mu. In other words, the test and the interval lead to the same conclusion about the null hypothesis, but the confidence interval provides much more information. It gives us a set of plausible values for the population mean. The connection between two-sided test and confidence intervals is even stronger for means than it was for proportions. That's because both inference methods for means use the standard error of the sample mean in the calculation. Notice for my test statistic t, the denominator is s sub x divided by the square root of n, and for my confidence interval, my standard error is s sub x divided by the square root of n. These two values were not the same when we were dealing with proportions. One involved our hypothesized p naught value, and one involved the p hat value. A two-sided test of significance level alpha and a 100 times 1 minus alpha % confidence interval give us similar information about the population parameter. When the two-sided significance test at level alpha rejects the null hypothesis, the 100 times 1 minus alpha % confidence interval for mu will not contain the hypothesized value. When the two-sided significance test for alpha fails to reject the null, the confidence interval will contain the mu naught value. Now we're going to take a look at another method of finding an inference for means, and this time we're going to be looking at something called paired data. An example of this would be possibly taking a pre-test and a post-test and trying to compare the difference between the two. Comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Studies designed that involve making two observations on the same individual, or one observation on each of two similar individuals, like twins, results in what's called paired data. When paired data results from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the difference in each pair. If the conditions for inference are met, we can use a one-sample t procedure to perform inference about a mean difference noted as mu sub d. And we would proceed using our one sample method that we've already done. These methods, however, when we're pairing data like this, are sometimes referred to as paired T procedures. Let's look at an example. Researchers designed an experiment to study the effects of caffeine withdrawal. They recently recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subject took capsules containing their normal caffeine intake. During another 2-day period, they took placebo caplets. The order in which the subject took the caffeine and the placebo was randomized. At the end of each of the 2-day period, a test for depression was given to all 11 subjects. Researchers want to know whether being deprived of caffeine would lead to an increase in depression. Below to the left, you can see a table for each subject. If caffeine deprivation has no effect on depression, then we would expect the actual mean difference in depression scores to be 0. We want to test the hypotheses. H naught is the mean difference is equal to 0, and the alternative would be the mean difference is greater than 0, where mu sub d is equal to the true mean difference, placebo minus caffeine, in depression score. Since no significance level is given, we will use the default value of alpha is equal to 0.05. We must check to make sure the conditions are met. Again, we need to make sure that we have randomization. Since the researchers randomly assigned the treatment order, placebo then caffeine, or caffeine then placebo, randomization is taken care of. Since the number in the sample was 11, we need to examine the data to see that it's safe to proceed with T procedures. Remember, the original population must be normal, and we don't know that, or the number in the sample must be greater than or equal to 30 for central limit theorem to work. In looking at these, the histogram has an irregular shape with so few values. The box plots show some right skewness but no outliers, and the normal probability plot looks fairly linear. With no outliers or strong skewness, the T procedure should be pretty close to accurate. We aren't sampling here, so it's not necessary to check the 10% condition. We will assume that the change in depression scores for the individuals are independent. This is reasonable if the experiment was conducted properly. The sample mean and standard deviation of the difference x bar sub d would be 7.364 and s sub d would be 6.918. My test statistic t would then be 7.364 minus my hypothesized value of 0 divided by 6.918 over the square root of 11, or 3.53. When I find the probability of my t-score being greater than 3.53 using a degrees of freedom of 10, I find the value of 0.0027. With a p-value of 0.0027, which is much smaller than our chosen alpha is equal to 0.05 level, we have convincing evidence to reject the null hypothesis that there is no difference. We can therefore conclude that depriving these caffeine-dependent subjects of caffeine can cause an average increase in depression scores. Let's talk about using these tests wisely. Go ahead and pause the tape for a minute and read through these 2 paragraphs. Using tests wisely is not so simple. Here are some points to keep in mind when you're using or interpreting significance tests. When the null hypothesis can be rejected at the usual levels, there is good evidence of a difference, but that difference may be very small. When large samples are available, Even a tiny deviation from the null hypothesis will be significant. Don't ignore lack of significance. There is a tendency to infer that there is no difference whether a p-value fails to attain the usual 5% standard. In some areas of research, small differences that are detectable only with large sample sizes can be of great practical significance. When planning a study, verify that the test you plan has a high probability of detecting a difference of the size you hope to find. Statistical inference is not valid for all sets of data. Badly designed surveys or experiments often produce invalid results. This goes back to the garbage in, garbage out principle that we talked about first semester. Beware of overanalyzing or multiple analysis. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance might have little meaning. We have now completed our look at inference for one population or one sample. Chapter 10 will look at comparing two populations or groups or two samples.